Okay, so we have exponential functions today. We are going to graph exponential functions and solve exponential applications. Okay, so for the first one, it tells us to graph each of the functions and write the domain and range and the y-intercept. So we are given f of x equals 2 to the x. Okay, so if you ever need to graph something, the easiest thing to do is make an XY chart. So let's just say X, Y. And the best numbers to choose, if you have no idea what to choose, is -3 to +3. So we're going to do -3, -2, -1, 0, 1, 2, 3. Okay. And then we're going to take all of these values and plug them in for x into this exponential function 2 to the x. Okay, and that's why I pulled up Desmos, so we can make that easier. So I'm going to type this function in, 2 raised to the x. And then I'll hit the little gear icon, make the table, and type in those exact numbers that I wrote. -3, -2, -1, 0, 1, 2, 3. So here we have 0.125, 0.25, 0.5, 1, 2, 4, 8. Okay, and we'll go ahead and graph this. So at -3, we're at 0.125, so that's like 0.13. So at -3, we're just going to be right above the x-axis. And then at -2, you're at 1/4. So that's not much higher than the last point. So we'll just put it there. And then at -1, you're at 0.5. So I'll put that in the middle. And then 0, you're at 1. 1, you're at 2. 2, you are at 4. And 3, you are at 8. Okay. And here's what our graph's going to look like. It's going to be really, really close to the x-axis. And curve up and to the right. So this is the graph of the exponential function 2 to the x. So as you see, as the graph goes to the left, it gets really, really, really close to 0, but will it ever touch 0?
Nope.
Nope, it will never touch 0. It'll get really close, but it will never touch 0. And then as your x values go out to the right, your y values start to get larger and larger and larger. Okay, so the domain for all exponential functions, any exponential function, the domain for all exponential functions is -infinity to infinity. That is always the domain for exponential functions. Now the range, well, since it gets really close to 0, but we'll never touch it, the range for this exponential function will start at 0 and not included because we're never going to touch it. And it's going to head towards infinity. So it's 0 to infinity. And then looking at our y-axis, we have a y-intercept at 0, 1. Okay, and that is the graph of the exponential function 2 to the x. And functions in this form, like 2 to the x, 3 to the x, and the next one 5 to the x, 5 to the x, they're all going to look really similar. Okay, any questions on number 1? Everybody good with that?
Yeah, I think we're good.
All right. So 5 to the x, we're going to do the exact same thing. So 5 to the x, we again make our XY chart, and we'll pick the same numbers. -3, -2, -1, 0, 1, 2, 3. Okay. And let me change my function. I'm just going to type on Desmos 5 to the x, hit the gear icon, table, and do it again. -3, -2, 0, 1, 2, 3. So at -3, you're at 0.008. Then 2, 0.04, 0.2, 1, 5, 25, and 125. Okay, so we're not going to be able to fit the last two on our graph, but again, it's going to look very similar to the graph that we just did above. So graphing this, -3, you're at 0.008. This means you're like really, really close to the x-axis. And then -2, you're not much higher. And then -1, just a little bit higher. And then 0, you're at 1. And then 1, you are at 5. So here's what our graph looks like. Comes from the left and shoots upward, just like the last one. This one looks a little steeper than the one above it. So, okay. And again, to keep it simple, the domain of any exponential function, -infinity to infinity, the range, and I'm going to say the range of a basic exponential function. When I say basic, like 2 to the x, 5 to the x, 3 to the x, is always going to be 0 to infinity. And my y-intercept, again, is at 0, 1. Okay. Everybody go with that? Okay. Let's do it one more time. So we have 3 to the -x. So we'll do the exact same thing here. XY chart. And pick our favorite numbers, -3 to +3. Okay. And this time that x is negative. So 3 to the -x. Make my XY chart and do our numbers. -3, -2, -1, 0, 1, 2, 3. Okay. So at -3, we get 27, 9, 3.
I have a question.
What's up?
On the homework, should we do -3 to 3? Or like, do we need to have like at least like 5 numbers, or how much?
I would keep it -3 to 3.
Okay, cool.
Yeah. 0.037. Just having, because the more x values you pick, the more information you have on the graph. And since you're seeing these graphs for the first time, it's just good to pick -3 to 3, because that gives us enough information to know what the graph is doing. Okay. So we're not going to be able to fit -327 on here, but we can fit -2 and 9. So -2 and 9, and then -1 and 3, and then 0, 1, and then 1 and 0.33 or 1/3. So that's going to be just below half, and then 2 and 0.11, lower, and then 3 and 0.037. There we go. So now this graph will come down and head to the right. Okay. And again, the domain for all of these exponential functions, even if the exponent is negative, is still all real numbers. So -infinity to infinity. And the range, so this one was a little different, but it's still the same. So as your x values go to the right side, your y values get closer and closer to 0, but again, will they ever touch?
Of course not. 0 is overrated.
There you go. And 0 to infinity. And again, we have a y-intercept at 0, 1. Okay. So if you notice the difference between this exponential function and the others, these two exponential functions are increasing functions. They are all increasing functions. Both of these are. The third one we just graphed is an all decreasing function. Okay. Just something special to note about those. All right. Everybody good with that one?
Yes.
All right. Got some thumbs. Got a yes. Perfect. Now let's move on to some exponential applications. So we're going to get into money math, which is going to be fun. So we need to know the simple interest formula, the compound interest formula, and then I think the continuous compound interest formula. So good thing I teach business math, or I would not know what any of these formulas are. So the simple interest formula is given as A equals P times 1 plus RT. And what this formula does is calculate the interest that you will either gain or have to pay if you invest or take out a loan. That's what the simple interest formula does. So say you take out $1,000 at a rate of 5% over 10 years, this formula will calculate how much interest and how much you'll pay in the end. So down here, we'll fill in what A, P, R, and T are. Okay. So now compound interest formula is given as A equals P times 1 plus R over N to the N times T. Now this is a cooler formula because now let's say you invest $1,000 and this $1,000 is getting interest at a rate over a certain number of compoundings. And compoundings mean that you are making interest either every day, every week, every month, or every year. That's what it means to have compound interest. So, or every quarter, whatever time periods are within a year, days, weeks, months, quarters, semi-annual or annual. So that's what compound interest does. So now to put labels on everything that you see, A is always the final amount. P is always the beginning amount. R is for rate. T is for time. And N is for the number of compoundings. And usually time in these type of problems is always in years. So if it's not in years, we have to convert it to a year. So I'm just going to say that in years. Unless the problem states it different. If the problem wants it in days or months, we can keep it like that. But usually T is always for time in years. Okay. Everybody got those formulas down? Definitely something new if you haven't seen them before. So we're going to practice them. Okay. All right. And here's what I was talking about, compounding. So if you're going to use that compound interest formula, you need to know what compoundings you're working with. And it's every time period within a year. So if we are compounding annually, this means you are earning interest every year. So if it says compound interest is annually, that means N is going to be 1. If compound interest is semi-annually, this means you're earning interest twice a year. If your compound interest is quarterly, how many quarters are in a year?
4,
4.
right?
Yep, 4. Every 3 months, right? And then month, how many months are in a year?
12,
And how many weeks are in a year?
52,
52, very good. And let's say we said we were doing compoundings daily. How many days are in a year?
365,
365. There you go. And if it's anything else, we could figure it out. Okay. So that's how you figure out your compoundings. The problem will tell you as well. It's going to say, how much will you make if you compound monthly, quarterly, daily, weekly? So it's going to give us that amount that we need to do. Okay. All right. So now let's say you don't want to use compound interest. We want to use something that is called continuous compound interest. And what's cool about continuous compound interest is that your investment is making money every second, every minute, every hour, every day, every week. So it's like interest on top of interest on top of interest. And it sounds great. It sounds like if we put $1,000 in, we'd be millionaires by tomorrow, but it doesn't work that way. There are caps and well, actually the cap would be the rate you're getting on your investment. So yeah, your bank will be like, yeah, we'll do continuous compound interest for you, but we'll give you a rate of like 0.01%. And you're like, I'm not going to make anything with that. But maybe that's how the money market accounts work. That's why you make very little on money market accounts. But this is the continuous compound interest formula. It is A equals P times E raised to the RT. So continuous compound interest is known as our best friend, Pert. So Pert is good. And what is cool about Pert is this formula, if in context of growth or decay models in biology, it can tell you how long something's been dead for, such as dinosaurs or like ancient hunting tools, anything like that. Or it can tell you how fast a bacteria population, an animal population, a human population will grow over a certain amount of time. So it's actually a really cool formula. And it's even cooler when you apply it to money. That's what we're worried about, right? So this can tell you how exponentially your money will grow if you invest it correctly. Okay, so those are our 3 formulas. You have simple interest, compound interest, and you have PERT, continuous compound interest. So let's try these out. All right, so B, you have invested $100 earning 2% interest. See, there it is already. 2% interest, we don't have a deal. We're not going to make any money off 2% interest, but that's another day. So we're investing $100, earning 2% interest. How much will this be worth in 15 years if interest is simple? So here we use the simple interest formula. So A equals P times 1 plus RT. And it's good to, again, label everything we have. So the beginning amount, we are putting in $100. The rate we're getting is 2%, but remember, you always convert to decimal. And the time we're getting is 15 years. So we have everything we need to plug in, P, R, and T. So we'll have A equals 100 times 1 plus R, which is 0.02 times 15. and you will type it in your calculator exactly as I wrote it. Okay, I don't think I need the graphing calculator. I just need a scientific. There we go. So you're going to type it in just like I wrote it. 100 times 1 plus 0.02 times 15. And if we invest $100 at 2% interest for 15 years, at the end of that 15 years, we'll make $130 gains. That's what I'm talking about. 15 years to make 30 bucks. What do y'all think about that?
Not good.
Not that much.
Not that good. Hey, it's free money though, right? Okay. Now we want to know compounded annually, monthly, weekly, and then continuously. So for these three, we're going to use that compound interest formula. I'll just write it over here. A equals P times 1 plus R over N to the NT. Okay. So again, label everything we have. P is 100. The rate is still 0.02, but now we are compounding annually. So that's the new one we throw in there. N is going to be 1, and then time is still 15. Okay, we have everything we need. So plug it in. A equals 100 times 1 plus 0.02 over 1 raised to the 1 times 15. Okay, so we can make this a little pretty before we go and type it in. I'm just going to rewrite this as 100 times 1 plus 0.02 to the 15th. You can even write the 1 plus 0.02 as 1.02. So here's how I'll type that in. 100 times 1.02 all raised to the 15th. Look at that. Now, if we find a better bank that lets us compound annually, meaning this investment gets interest every year for 15 years, we'll make $134 instead. That's definitely better than 130, guys. All right, but still, we need to find a better way to invest our money. Okay, so now we want to do compound monthly. So we know everything. P's the same, R's the same, N's the same. I mean, not N's the same, T's the same. But now we compound monthly. So the only thing we need to change is that N is now equal to 12. And we're still using this information. So it's going to be A equals 100 times 1 plus 0.02 over 12 raised to the 12 times 15. Okay, now we can type it in just like I wrote it. So 100 times 1 plus 0.02 over 12 raised to the 12 times, make sure that doesn't move. It keeps moving. So I'm going to put it in parentheses so it stops moving. Times 15. There we go. Why not? Let's put that in its own parentheses because every time I hit the times button, it moved back to the middle. So we don't want that to happen. Okay. So now, if we tell the bank, hey, we don't want to compound annually. We want you to compound the money monthly. We want interest every month because that sounds like the better deal. And if we do that, oh, I left the decimal number off on that one, huh? Hang on. We want all our money. So that was 134.59. There we go. Yeah, keep those decimals on there. And now if we compound every month, we'll make 134.95. About 40 cents more, guys. All right. So if anything, these examples should be telling you invest your money better. We don't want to wait 15 years to earn 34 bucks. Trust me. Okay. And then we compound weekly. So this means N is 52. And same numbers. A is 100 times 1 plus 0.02 over 52 raised to the 52 times 15. All right, we're like, you know what? We're not going to get enough money. How about we compound weekly? Because now I want to make money every week. And let's see if that changes. It's not, but it'll be a small difference. 52 times 15. And look at that, guys. If we go to weekly, we'll make 134.98. 3 cents more than the last one. Okay. And now the last one, we're like, you know what? We're not going to make money compounding annually, compounding monthly, compounding weekly. So let's go ahead and try to make money every second, every hour, every day, working all the time. Interest on top of interest on top of interest. So this last problem is going to use our best friend, Pert. So again, P is still 100. R is still 0.02. And time is still 15 years. So you get A equals 100 times E raised, I'm going to put parentheses, to the 0.02 times 15. All right. So when you type this in, again, type it in now as I wrote it, 100, and you're going to type the letter E times E raised, and I'll do my parentheses, 0.02 times 15. Look at that. And now our money's making interest every second, every hour, every day. And at the end of the 15 years, we have 134.99. We have a penny more than what we would get weekly. All right. So the lesson to be learned here is don't make an initial investment of 100 and just let it sit there. Add $100 a month. Add $100 every 2 weeks. And every time you add that money, you will definitely gain more interest. And at the end of that 15 years, you'll be rich. So everybody go with this page.
Yep.
All right. Okay. Another invest. What do you guys think? Do it or skip? It's the same thing as what we just did.
I vote skip, but like someone else say something if they need to look it over again.
What do you guys think?
Do it again.
Do it again. All right, there we go. Let's do it again. Okay. So 5. If you invest $800 for 5 years at 2.5% interest, how much would you end up with simple, annual, monthly, weekly, hourly, and continuously? Okay, let's do it. So again, first one, simple interest, which is the A equals P times 1 plus RT. And the initial investment is $800. The rate is 2.5%, so 2.5%, which always convert to decimal. And then time is 5 years. Okay. You get A equals 800 times 1 plus our rate, 0.025 times 5. And let's see how much money if we just let it sit there. No compoundings, no nothing. just sits there and gains interest. 1 plus 0.025 times 5. And we'll have $900 in 5 years. So we'll make $100 in 5 years. So that's like $20 a year. Still not what we want, but maybe it can get better. Okay. Compounding annually, compounding monthly, weekly, hourly. All three of these use that equation. P times 1 plus R over N to the NT. And again, P is 800. R is 0.025. Now we're compounding annually. So N is 1 and time is still 5. Okay. Put it together. 800 times 1 plus 0.025 over 1 raised to the 1 times 5. Okay. And let's see what we got. 800 times 1 plus 0.025. I'm just going to leave it at 0.025 because that over 1 is itself. And then all raised to the 5th. We'll make $905. So 905.13. Okay. So that's annually. Then monthly, the only thing that changes here is 12. And that'll be A equals 800 times 1 plus 0.025 over 12 raised to the 12 times 5. Okay. So 800 times 1 plus 0.025 over 12 raised to the 12 times 5. That's 60. So I'll just do 60. And you'll make 906.40. Hey, getting better. And then next is weekly, which is 52. So A would be 800 times 1 plus 0.025 over 52 raised to the 52 times 5. Do it again. 800 times 1 plus 0.025 over 52 raised, and I'll do my parentheses here, 52 times 5. So I'm going to put parentheses there. Why not? And we'll have 906.49. Okay, here's one we haven't found out. Compounded hourly. Somebody find out how many hours are in a year. Ask Google or ask Siri or ask Alexa. Ooh, I have Alexa right here. Alexa, how many hours are in a year?
8760.
8760. There we go. That doesn't seem very many hours for 1 year, but it's true. So you'd have 800 times 1 plus 0.025 over 8760 raised to the 8760 times 5. Okay. So 800 times 1 plus 0.025 over 8760 raised to the parentheses 8760 times 5. And you get 906.52. Just 3 cents more if you were compounding weekly. My goodness. We need to learn how to invest better, guys. And of course, last one is Pert. So P is still 100. Rate is still 0.025, and time is just 5. So A equals, oops, not 100, 800. 800 e to the 0.025 times 5. Okay. 800 e raised to the parentheses 0.025 times 5. And we get 906.52. Hey, same as hourly. Okay. There you go. That's how you use the simple interest, compound interest, and continuous interest. Everybody go with that.
Professor, I
Mhm.
just have a question. So I see that you're using Desmos, but is there like a tutorial, like a basic 101 on how to use like the raise and all those functions?
Oh, like to raise the exponent?
Yes.
If you're using your computer, are you using a computer or using like a regular old calculator?
No, computer.
Computer. So if you're
Mhm.
just gonna raise it, just hit the shift button and the number 6. You see a little caret button? The little,
Yes.
yeah, that's how you raise it to the exponent.
Wonderful.
Or
Thank you.
Also on the computer page, the A to B.
yeah, right down here, right?
Yeah.
So also Desmos has it too on the main keyboard. So let's say I had 5 and I wanted to raise it to something, that little A to the B button, you just click that and it'll let you type in an exponent. So either one works. Shift and number 6, or hit that A to the B button that's down there.
Thank you.
Yeah, for sure. Okay, cool. All right. 6. The growth of a bacteria colony can be modeled by the function below, where n is the number of bacteria in thousands and t is the time in minutes. What is the initial population of the bacteria? Okay.
I have a question
What's up?
too. I was wondering if you could post the homework, because I kind of already understand these problems because I've done them before. So I kind of like want to do something.
Okay.
But if not, that's fine.
Have I not posted the homework? I'll double check.
No, the last thing I saw was polynomials and rational functions on the assignment.
I can see the homework on my end. It's page 177.
Okay.
Yes.
So yeah. Okay. I mean, if I haven't posted it, remember you can reference the schedule to find out where to find it in the packet. But remind me again at the end if I haven't posted the homework. I thought I did though.
I got it off of modules, and then you
Module.
just like scroll down.
Okay.
Mhm.
So then if you can see it, good. Okay. I'll just
Oh,
double
you
check
right,
it
my
later.
bad. I found it. Thank you.
Okay. Good. Okay. So we want to know, what is the initial population of the bacteria given this model n equals 25e to the kt? Let's see. So if no time has passed, what would we plug in for t? What represents nothing?
0.
0. So to find your initial population, you would just have n equals 25e to the k times 0, which would give you 25 times e to the 0. And if I type that in on our calculator, I'd have 25 times e raised to the 0, and we would just get 25. Or there's an easier way to think about this. This is very similar to Pert, to A equals P times e to the RT, where if you remember this formula, P is the beginning amount. So if you reference this one, 25 would have been the beginning amount. So that's a lot easier to state than plugging in 0 and having to figure that out. But either way works. Okay. Now B says, if the growth rate is 1% per minute, how many bacteria would we have after 2 hours? So here they're giving us a rate and they're giving us time. So the rate is 1%, which we change into 0.01, and time is 2 hours. But if we read the problem again, time has to be in minutes. So how many minutes is 2 hours?
120.
120 minutes. Okay, we have all the information we need. So this means that N equals 25 times E to the 0.01 times 120. And this will give us the bacteria after 2 hours. So let's see, 25 times E, raise it, and then parentheses, 0.01 times 120. And this bacteria would be 83. It's just 83, right? It would be 83. So this is the number of bacteria in thousands. So not only would it be 83, but you would have to multiply it by 1,000. And this bacteria would actually grow to a colony size of 83,000 bacteria. Heal. Wash your hands, right? Okay, everybody go with that one? Yeah. Let's keep rolling. All right. 7. Suppose that $7,000 is invested at an annual interest rate of 5% compounded daily. Find the total amount in the account after 12 years if no withdrawals are made. So this will use the compound interest formula. And the easiest giveaway to know what formula you're using is look for the words. So it says we are compounding daily. So if you are compounding over a certain amount of time, this means you will use the compound interest formula. 1p times 1 plus r over n to the nt. And now we just label everything we're given. The beginning amount is $7,000. The rate is 5%, so 0.05. We are compounding daily. There are 365 days in the year, and we are doing this for 12 years. Okay. Plug it in the formula. A equals 7,000 times 1 plus 0.05 over compoundings, 365 raised to the 365 times 12. And let's see how much money we have after investing $7,000 for 12 years. So 1 plus 0.05 over 365, oops, over 365 raised to the parentheses 365 times 12. Ooh, that's nice. So after 12 years, your $7,000 will turn into $12,754.31. Now that is much better than the last examples, huh? But I mean, still not great. It's 12 years and you only earn $5,000. It's free money though, but we could always do better. Okay, everybody go with that one. All right. Again, just look at what the question's asking and you will know which formula to use. So in 8, it says that suppose that $10,000 is invested at an annual interest rate of 4.14%. I hate how they write it like that. Just say 4.25%. Okay. Compounded continuously. So see those? Compounded continuously means we get to use our best friend, Pert. Find the total amount in the account after 35 years if no withdrawals are made. So label everything. We invest $10,000.
I have a question.
What's up?
E in this formula is like the log form E, like natural log, where it's like exponential. Is that what that is?
It is, so E is E. So E is its own base, but it has an inverse,
Yeah.
which is a log. Yes.
Gotcha. And it's the one that you have to find in miscellaneous on Google, on Desmos, right? It's just like the little E
No,
symbol.
you just type in E.
Oh, okay, cool.
Yeah, just hit the letter E and that makes your base. Okay. So we have the initial amount, 10,000. We have the rate at 4.25%, and we are doing this for 35 years. Okay. That's all we need for Pert. That's why he's great. That's why he's our best friend. So you say A equals 10,000 times E and raise it to the 0.0425 times 35. And put that in parentheses. So type this one in, 10,000, hit E, and then raise it to the 0.0425 times 35. And we will earn $44,260.17. And that's after 35 years. So in 35 years, you make $34,000. But still good. Okay. So that one we use Pert. And now the next one, we have an investment property in 2016 was worth $375,000. If it decreased in value at a rate of 3.5% a year, compounded annually, what would it be worth in 2030? Okay, so look at those special words, compounded annually. That means we use the compound interest formula. Okay. And the investment property was worth $375,000. So that's our initial amount. $375,000. We decrease in value at 3.5%. So this is going to be negative 3.5% because we are decreasing. So that'll be negative 0.035. And then we are compounding annually. So N is 1. And we are doing this if it was in 2016 and now we're in 2030. How many years is that? Or what's the difference in years?
14.
14. There we go. Okay. Now plug it in. A equals 375,000 times 1 plus negative 0.035 over 1 raised to the 1 times 14. Okay, let's see how much this investment property is worth in 2030 if its rate keeps decreasing. So 375,000 times 1 And that's going to be just negative 0.035. So I'm just going to write it as 1 minus 0.035. 2, good, raised to the 14th. And in 14 years, this investment property will be $227,726.54. So this investment property is losing its money somehow. Okay. Everybody good with that page? Okay. All right. What do we have? What do we have? More. Okay. 10. Tim is trying to decide which loan is better. Bank A offers a 15-year loan at a rate of 4.5% compounded weekly, while Bank B offers a 10-year loan at a rate of 5.75% compounded continuously. Tim wants the loan that will result in the lowest total owed. If he is borrowing $4,800, which loan should he take? Okay. Well, we're going to use compound interest and we're going to use continuous compound interest in this problem. So let's look at Bank A. All right, so Bank A, first off, we are compounding weekly. So Bank A is going to use the compound interest formula. And let's see. We want to borrow $4,800. So there's our initial amount. $4,800. And Bank A will give Tim a rate of 4.5%. So 0.045. And we are compounding weekly. So N would be 52. And Bank A says they can do it for 15 years. So time would be 15. Okay. So for Bank A, you'd have A equals 4,800 times 1 plus 0.045 over 52 raised to the 52 times 15. Let's see how much Tim would owe if we went with Bank A. 4,800 times 1 plus 0.045 over 52 raised to the 52 times 15. So with Bank A, at the end of the 15-year loan, Tim would actually have to repay $9,424.61. So Bank A is going to make him pay almost double what he took out in interest. Bank A is not looking good, guys. Now, let's check out Bank B. And Bank B, we are compounding continuously. So that means we get to use Pert. And we are borrowing $4,800. But Bank B will give us a rate of 5.75%, so 0.0575. And Bank B will give us a 10-year loan. All right, let's see. A equals 4,800 times E raised to the 0.575 times 10. Let's see. 4,800 E raise that to the 0.0575 times 10. And if he goes with Bank B, he'll only have to repay $8,530.20. So he'll still pay almost double, but definitely less than Bank A. So it looks like Bank B is our obvious choice, or our obvious choice is don't take out this loan, Tim. Okay. Everybody go with that one. That's like student loan interest right there, guys. Take out a $4,800 student loan. You actually probably pay triple back. Okay. Next, 11. The amount of plutonium remaining from 1 kilogram after X years is given by the function W of X equals 2 to the negative X over 24,360. How much will be left after 1,000 years? So in this problem, X represents the amount of years. So if they're giving us 1,000 years, what do we plug it in for?
X.
X. So you'll get W of 1,000 equal to 2 to the negative 1,000 over 24,360. Okay. And typing that in, it is 2, and you will raise it, and I'll type in negative 1,000 over 24,360. And after 1,000 years, there will be 0.97, and the amount is in kilograms. There will be 0.97 kilograms of plutonium left. Hey, not bad from 1 kilogram. You only lose 0.03 over 1,000 years. Insane. What's up?
I have a question.
It better be over this. We're almost
It's over the
done.
homework.
Well, ask me after I'm done.
Okay, gotcha.
Okay. So next is after 10,000 years. So again, you'll plug in 10,000 for what?
X.
X. So you have W of 10,000 equal to 2 to the negative 10,000 over 24,360. And all I'm going to do, cheat code here, look at this. Just go back to what I typed in Desmos and add a 0 to the numerator. And after 10,000 years, you'll have 0.75 kilograms. Okay. Everybody go with that one. That wasn't bad. That was easier than the other ones we've done today. Okay. Hey, look at that. Last one. I thought there was more. Okay. 12. The function m of h equals 10 times e to the negative 0.173h can be used to find the number of milligrams m of morphine that is in the patient's bloodstream h hours after the drug has been administered. Okay. So what was the initial dosage? So once again, you can compare this formula to Pert. So looking at this, what would be the initial dosage of morphine?
10.
10. Good. So the initial dosage would be 10 milligrams because 10 is your initial amount or your beginning amount. Okay. And then how many milligrams will be present after 1 hour and 4 hours? Well, we plug 1 and 4 in for which variable?
H.
H, right? So you'd have M of 1 and you'd have 10 times e to the negative 0.173 times 1. And why not do them both at the same time? 4, 10 times e to the negative 0.173 times 4. Okay. Typing that in, just like I wrote it, 10 e raised to the negative 0.173. That'll be for the first one, because 173 times 1, the same. But again, if we're multiplying, why not keep that in parentheses? Times 1. And after 1 hour, there will be 8.41 milligrams of morphine left. And then after 4 hours, so all I'm going to do is go back to what I typed in Desmos, delete that one, put a 4, and after 4 hours, there will be 5.01 milligrams of morphine left. All right, guys. That was exponential functions. Everybody good with that?
Yes, Professor, I have a question.
What's up?
So I haven't used Desmo very much. I did use it for the last homework, and I had a problem trying to do the division in the parentheses.
Mm-hmm.
How do I
So
instruct
like,
it, or how does it know that I need it to be divided?
so like inside the parentheses, like
Yes.
let's say for this example that I wrote here.
Yes.
Okay. So when you're typing things in, so let's say I just rewrite that problem, 4,800, you'll put a parentheses, and then I'll say 1 plus, and after you hit that plus sign, hit your backward slash on your keyboard. Backslash, and when you do that, it should create a fraction for you. Or
Perfect.
using Desmos, you see that little division symbol there?
Mm-hmm.
Click on that, and it'll do that for you as well.
Okay,
So, yeah.
wonderful. Thank
Yeah,
you.
yeah, for sure. Yeah, if anybody else is having calculator problems, let me know. We can hash them out. I can tell you how to do it.
I am having a calculator problem.
Okay. What's up?
So you know how earlier when we were doing the graphs and we make a table for it from -3 to 3? I'm putting like at my y, like then our whatever it was. So like one of them is like 3 to the power of x, but it's like not working.
Did
Like
you
I don't
make
know how
sure if you typed it in right, you have it as 3 raised to the x like that,
Yeah.
and then you hit the table and you type the -3. So just make sure you're typing everything in the right way.
3.
So-
Okay. Okay, yeah, just kidding. It's working out. I don't know what I was doing before. I did the same thing, but
Nope.
now it's
Oh,
working.
good. Probably just a typo somewhere.
Thank
Okay.
you.
All right, guys. Well, we're done. So if you have questions, stick around. If not, see you on Wednesday.